Okay, this is our first PowerPoint for Unit 1, Atomic Structure and Properties. This slide shows you all the different topics we will be discussing, and really these first two should be a review. We'll briefly talk about the composition of a mixture, but I think when we get to electron configuration, there might be one or two new details for that. I would think that this instrumentation of mass spectroscopy and PES will have a lot of new information, and then periodic trends will be kind of a combination of things you learned in the first year class, and maybe the explanations of those trends would be the new topic. So these are all the things we'll discuss. The mole, as you see, and I really like this diagram, there are a lot of ways we can either start with particles or a mass or even a volume and calculate moles, or we could go the other way. So if you notice, these very faint arrows show you which way. So here, if we started with moles, we'd be using this and multiplying to get one of these particle values. But if we started with a particle amount, we would be dividing by Avogadro's number. So that's, a calculation you will be doing in this unit. And then mass to moles is probably the most common calculation that we do in chemistry. I feel like you would be very familiar with that. Maybe just a quick review would be helpful. Or if we had moles, we could change to molar mass going the opposite direction. I did want to say that using a volume in either, as you notice, this is really for a gas, that's the molar volume of a gas, or as I mentioned here, molarity and PV equals nRT, all three of those conversions will be covered in Unit 3. So really we're just talking about Avogadro's number and molar mass calculations. So once we can do those simple calculations I mentioned on the previous slide, we'll be doing other things with them. So for percent composition, we'll need the molar mass of the elements that are in the compound to divide it by the total mass of the compound to figure out, maybe a percent of an element in a compound. Empirical formula is when we have percents, or maybe we don't even have percents. We might even have masses or even moles to start with, but we were trying to determine the simplest whole number ratio of elements in the compound, which is the definition of empirical formula. And the molecular formula, we would have to be given the mass of a molecule, and if we knew its empirical formula, we could figure out what integer to multiply by to get this new formula. So let me kind of give you an example here. So if I said I have CH2O, that's the lowest whole number ratio, so that would be an empirical formula. If I have some multiple of that, which probably looks familiar, glucose, that is a molecular formula. So completely different molecules, but they're related because if we reduced this, we would have the same empirical formula. And percent composition is based on the law of definite proportions, and you probably learned about that in the last year class. It's just the ratio of the mass of the constituent elements in any pure sample of that compound is always the same. So if we have, as this example shows, potassium permanganate, we always have to have these percentages of the elements in the compound for it to actually be that actual compound. For the empirical formula, this is a very helpful, just short little rhyme to remember. If we have percents of elements in a compound, we would change those to their masses by just assuming a 100-gram sample. But a lot of times that don't even start us with percents. We might be starting with grams of the elements in a compound. So if we have masses, all we have to do is change those to moles. And then once we have moles of each, as you see here, moles of each element, we see which of those mole values is the smallest and divide it into everything. And that should give us whole numbers. Occasionally we might have to, if we had like 1.5, we might have to double that to get a whole number, and we'll see that later. But these would actually be our subscripts. So it rhymes: percent to mass, mass to mole, divide by the smallest, make it whole. And then here's the molecular formula example. Notice what was given is we have this empirical formula and we have the molecular mass. So this mass is the mass of the answer we're going to end up finding out. So the first thing to do, and sometimes this is difficult just because sometimes it seems like you don't have a lot of information, but one thing we can easily do, and this is how you're going to be able to solve this problem, is add up the mass, which we'd call the empirical mass, of the empirical formula. So that's what we've done here. There's 1 carbon, 4 hydrogens, and a nitrogen. So that empirical formula has a mass of 30. Well, 30 goes into 60 twice. So that tells us if we double our empirical formula, that will give us our answer for the molecular formula. Okay, a couple slides on the composition of a mixture. Unlike a compound that has, based on the law of definite proportions, the exact same percents of elements in the compound every time we have some of that compound, with a mixture there's going to be some varying proportions. Okay, we can do elemental analysis to determine the numbers of atoms in a substance, and therefore we can figure out its purity. So here's an interesting example. It says a sample of carbonate rock is a mixture of these two compounds, calcium carbonate and magnesium carbonate. The rock is analyzed in a lab, and the results are recorded in the table below. Calculate the mole ratio, and I'm going to underline this, of calcium to magnesium in the rock. So they're only concerned about the elements calcium and magnesium. So let's see what kind of data we have. We have the total mass of the sample, so that's everything together. We have the mass of carbon in the sample. And I'm thinking, do I even need to know the mass of carbon in the sample? And I'm thinking, they haven't asked me anything about carbon, so I'm thinking I'm not going to need to worry about that. I've got the mass of magnesium in the sample. Do I need to know that? Yes, that is going to be important because I have mass, I can easily change. It's because it's asking for a mole ratio. I can easily change that mass of magnesium to moles. And the next information is mass of calcium. Well, I am asked about calcium, so I do need to know that. Do I need to know the molar mass of carbon? No, haven't been asked anything about carbon. Would it be helpful, even though I should have a periodic table handy, to know the molar mass of magnesium and the molar mass of calcium? And the answer is yes. So let's think. If we need to make a ratio of calcium to magnesium, we need to change, and I'm going to start with calcium because that's the order. We need to change calcium to moles. So I'm dividing by molar mass. And then, and it's helpful to write the elements so we keep up with where we are. And then I've got the mass of magnesium. And then it's very nice, I was given the molar mass of that. So I'm dividing. So when I have these answers, I have 2 mole answers. So how should I answer the question? Well, whatever my calcium answer is, it's calcium 2, and you can write the word 2, or just make it a ratio to my magnesium moles. So if you look, here's it kind of written out neatly. So I've got 0.1 moles of magnesium. They solved that first, but the order that asked me for this is calcium to magnesium, so make sure you answer in that order. So it is 9:1. Okay, now we'll get into the quantum model of the atom, and this propeller blade example is really great because we really are not able to tell at any particular instant the exact location of an electron. So the propeller is really a great analogy to that. But really, what the quantum model helps us understand is that electrons can only have certain allowed energies, meaning they're only likely to be found in certain places in the cloud around the nucleus. And we call these orbitals and energy levels, and those are important terms, and make sure you don't use those interchangeably. Okay, the numbers 1 3 5. I'm sorry, let me go over here. The numbers like 1 and then 2 and then 3 and 4, those are our energy levels. The individual letters are orbitals. And sometimes people are calling energy level shells, and that's fine. And orbitals are the sublevels. So make sure you're not mixing up the terminology. This is a good video if you want to delve into that a little bit more. And this is what I'm sure you've done before. It's just the electron configuration. Again, the number tells us the energy level. The type of orbital really is a shape, but we don't really have to worry about that so much. But this is the type of orbital where that electron is located, and this is the superscript, is how many electrons are located in that place. So this is the first energy level is right outside the nucleus, and it only has this S sublevel. So as you go to each new energy level, it gets a little bit more complicated, and we have new sublevels. Here are the 3 types of configurations that you need to understand. On an AP exam, typically the most commonly asked would be to write an electron configuration of an atom or an ion. You could be asked, there's some questions, I know in the practice problems that use orbital notation, and that being able to draw that orbital diagram with these arrows. You might have been instructed to draw them like as half arrows. That's correct as well. They just need to have opposite spins. And you may not be drawing boxes. Like I teach my students to draw a line and label it as what orbital, and then, draw the electrons paired in it if they're enough to fill that orbital. And then the last one that is nice to know, and you might be asked to write noble gas, but this is just the shortened form of electron configuration. It's when you find a element on the periodic table, look at what noble gas comes before it. Like here, we would have, we know that is neon, and so we know that past that, we would know the electron configuration, if we shorten this, would be neon, 3s2, 3p6. So it's just not having to write the beginning of the electron configuration. And using the periodic table is that's the way I do it. I know some people use what we call an off-ball diagram, and it shows you the filling order as well. But if you can use the periodic table, it does really help. And if you notice, I like the way this is laid out because it shows you that every metal in group 1, the reason they have the same properties and are grouped together is because their valence electron is all the same, no matter if you're talking about the last element in the group or some other element. They all have one valence electron. That's what makes them have similar properties. So group 1, and that's the one electron they're going to lose to become an ion. Then we've got group 2, and then over here, typically we call this 13, 14, and then it numbers all the way to 18 with our noble gases. And one other thing to note is, remember, once you get past the 3rd period and you get down here to the 4th period, that's where the D block is one number behind. The 4s orbital actually has a little bit lower energy than 3D, so it does fill first. And notice that same pattern arises with the subsequent periods after 4. So here's some examples of the orbital diagrams for lithium. So that would be the 2nd period, and then sodium would start off the 3rd period, and their electron configuration. So if you've forgotten how to write those, this is kind of a good review of how the electron configuration corresponds to an orbital diagram. Notice, one thing to point out here is Hund's rule. Notice, since there are 3, I'll just take nitrogen for example, since there are 3 electrons in the p orbitals, based on Hund's rule, each orbital receives 1 electron before any orbital gets a pair. So if there's only 3, that means they each have their own orbital. We would not start pairing up if we get to oxygen, which is would be right after nitrogen. I just realized I skipped that. That oxygen would come back and start having a pair in that first orbital for its 4th p electron. So here's just some examples right at the ground state electron configuration for these neutral atoms. Okay, so look at your periodic table, find potassium. Notice it's in the 4th period, so we need to start at the beginning of the periodic table and record where all the electrons would go until we get to potassium's valence electron, which designates its group. So we have 1s2, then we're on the 2nd period, which starts with another s orbital, s block. Then if we keep using the periodic table as a guide, then we're to the 3rd period. Notice no D will appear until after the 4s orbital, but since potassium only has that its one valence electron in the 4s orbital, we are stopping there. And then if we look at neon, actually it's a little simpler. It has a total of 10 electrons. Notice these are ground state, just means that just refers to where the electrons have the lowest energy possible, which is what we would think of as our normal filling order. And these are neutral, so I should have said this earlier, but when we look at neutral atoms, we really just need to look at their atomic number, because atomic number identifies them for their protons, these atoms, but if they're neutral, they have that same number of electrons. So here for neon, I mentioned this a couple of slides ago, it ends in P6. Notice all noble gases, except for helium because it only has 2 electrons total, do have that octet. There's that 8 valence electrons. And so there we go. All right, now just if you saw orbital diagrams or you were asked to write an orbital diagram, it would look something like this. Again, a few differences. Some students are told to write blanks instead of boxes. I have a colleague who teaches her students to do the 3 boxes for like 2p stacked together. So it would look like this. It's really just probably what book you've used to learn from. These variations are fine. The most important thing is that the orbital is labeled and there is no subscript. With like in electron configuration, we would write 1s2. You cannot put the 2 here. It's the 2 arrows designate how many electrons have that energy. Now let's talk about ions. So if we look at, see now we don't have neutral atoms. We notice that oxygen is atomic number 8, but if it's has an overall -2 charge, let's think about that. That means it has it has 2 extra negatives. So that means it would have 10 electrons. So we would have to add these 2 extra electrons. So we should end up with 2. I mean, not adding 2, we will end up with 10. So notice that looks familiar. So oxide has that electron configuration, and then sodium is atomic number 11. It has an overall positive charge, which means it's lost an electron, and it also is going to have 10. So these 2, even though they're completely different ions, are going to end up with the same electron configuration, and we'll learn later on another slide, if you want to wait and write this in your notes, that is what the term isoelectronic means. Iso meaning the same. These are when ions or ions with a certain atom, like these are isoelectronic with neon, meaning they all have the same electron configuration. And there are the answers. Okay, this might be new from pre-AP chemistry. Just notice that iron, this and this is really only about, this slide's only about transition metals, so that would be our D block, elements that are in the D block. So here is iron's electron configuration, and when you study PES, you'll possibly see this example, but to form ions of a transition metal, this is the key, and I've underlined it. We need to remove the 4s electrons first. Okay, so here's a neutral version right here. So what we're saying is when it becomes iron 2+, notice it's the 4s electrons that are no longer there. Okay, because what happens is those electrons, the 4s electrons, actually take less energy to remove, and that's why they're removed first. Now, if we need to form the Fe3+ ion, 3 electrons have to be removed. So after the 4s electrons are removed, we will remove the third one from the D orbital. Okay? So I've given you like the electron configuration of zinc, and then I just want you to think about how should this, and if we rewrote all of this, and I get to 3p6, so let's just assume I wrote all this. It's kind of messy looking. Where should I take away these 2 electrons from? Well, hopefully, based on what we just talked about, you would say this. So it would just end 3p6, 3d10. Now when we looked at molybdenum, it's becoming a positive 5 ion, which seems crazy. But as we get to the end here, and again, I'll just rewrite 4p6, we would need to take away 5s, it's the last s orbital. Those electrons would be lost first, but then we still have to take away 3 more. So there would still be 1. So again, we take away 3 from there, there would be 1 remaining, and I would have to rewrite all this. So there you go for your final answer. Here are the examples of noble gas configuration. Notice what I've underlined is the electron configuration for neon, so you would just write neon in brackets and then what valence electrons are after that. For bromine, you would go all the way here, and that would be argon, and then you would continue with the other electron configurations. Here's the term isoelectronic, and you can see in context what that means is it's when all the things given have the same number of electrons. So it didn't matter if we have oxide or fluoride or neon or the sodium ion or the magnesium ion, they all have the same. This is their neutral atom electron configuration, but when they form an ion, they all end up with this electron configuration. Alright, so let's talk quickly about mass spectrometry or spectroscopy. You'll see it called different things. You really don't have to be able to explain how this is happening. Anytime you see this term, you need to think of isotopes. Okay, because the whole point, one of the uses of this is to separate compounds atoms according to their masses. So we're going to use it for this purpose, to figure out isotopes. So this is what this graph will look like. And I've asked you a few questions just so you can make sure you understand the graph. Notice we have this mass to charge ratio, and then we have this intensity. So notice that the taller the bar is, obviously that's going to represent some percent. Okay, so how many isotopes are represented by this spectrum? Well, I see 2 bars. That means this element has 2 isotopes. Which element does this spectrum represent? Okay, well, if I look at this masses, I see it's about 6 and 7. So if I look on my periodic table, what element has a mass between 6 and 7? Well, helium is 4, and beryllium is 9.01, so it must be lithium. Now, lithium's mass, when you actually look up, I'm looking at the AP periodic table, is 6.94. So notice it's between 6 and 7, but why is it so close to 7 because, these average atomic masses on the periodic table are weighted averages, meaning most lithium atoms have a mass of 7. Only 7.42% have a mass of 6. So that weighted average is going to be really close to 7. So let's quickly review how to calculate that. Now you would be given most likely very specific masses if they wanted you to use a calculator and do this, but when I set it up, the way this is set up works perfectly, but I go ahead and change my percents to a decimal. Okay, so I would say and this is like a fraction, my fraction of lithium-6, and so I'd multiply it, put a little star, times that mass, and then make sure you use order of operations. Then I would add, again I'm multiplying in the parentheses, change this percent to a decimal, star, I'm multiplying 7.016. So when I multiply inside each parentheses and add those two products together, I will get what I see on the periodic table. This is the same setup, I just did it slightly differently, and you must do order of operations, so it would be better if this had parentheses. Okay, PES is related to electron configurations, and then when we talk about ionization energy with periodic trends, it really supports that as well. So what's happening here, and it stands for Photoelectron spectroscopy, but it's much easier just to say PES. It's when high energy X-rays are basically knocking electrons out of the atom. Okay, and we know what energy these X-rays have. And so based on the energy the electron has when it's leaving the atom, we can tell, does it have little energy as it leaves the atom because it took so much energy to overcome the attractive force of the nucleus, or, maybe this was a valence electron because it didn't take much energy to remove it from the atom. So basically these graphs give us information about where electrons are located and what kind of energy they have. Okay, so the first time you look at this, you'll see these peaks. Okay, those are little, and this one has a 1 and a 2. What you need to look for is, and the first thing I look at is which of the peaks, and there could be many peaks, or in this case just 2, has the highest energy value. Okay, so notice this peak is 6.26. Whichever peak has the highest energy value, that tells you that is representing the first orbital. Why? Because the 1s electrons are the most attracted to the nucleus and would take the most energy to be removed, which is the definition of ionization. So notice there's a 2. How did we know that without a 2 being here and a 1 being written there? Well, it's the height. Look at the y-axis, relative number of electrons. It's the height of the peak. So we would expect, if there's more than one peak, that the first peak should be 2 electrons high. There should be 2 electrons in the 1s orbital if there's a second orbital. So what would we expect this second peak to represent? Well, think of electron configuration. What comes next? Well, that must represent the 2s orbital, and notice it's half as tall, so that just must be 1 electron there. So if knowing this electron configuration, we could figure out that is, from our periodic table, lithium. Okay, now let's look at another one. So this one has 3 lines of graphs. So again, like I said, find the peak with the highest energy value. So I'm looking around, and there's 3 different ones to look at, and I see this, 347. So I'm going to say, all right, well, that must be 1s. And if there's other peaks, that one must be full, because we're doing ground state. Then what's the second highest energy value? Well, I see 37.1. That must be 2s, and there are 2 electrons there, so that makes sense. So what would 29.1 be? Well, that must be 2p, And notice it's 3 times taller than the previous one, so that's 6 electrons. So this should make sense. First, the electrons in the first energy level in the s orbital are very close to the nucleus, very attractive, have the highest energy number. Notice that the s orbital is more attracted to the nucleus than the p orbital electrons. So its value is a little bit higher, but these are still closer together because they're close in proximity. They're in the same energy level. And so then we get down to the rest of this, and notice the numbers are dropping. So what we'd expect to be next? Well, 3s, 3p, and then that must be 4s1. Notice lowest energy value, that's going to be your valence electron. What element is this? Potassium. All right, and we could do this one quickly. Look for the highest number. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So this, notice, I just wanted you to see it could look like this, or in one graph together. You just have to look for the highest number and see which way the scale is going. Is it going like this one, high to low, or low to high, like we've seen previously?